Production of polyhydroxyalkanoates from Pseudomonas species for bioplastics. Bioplastics are natural polymeric materials that either have bio-based nature, biodegradable nature, or have both the properties, mean bio-based as well as biodegradable. Bioplastics can be derived from plants, animals, as well as microbial sources. Starch, cellulose, gums, resins are the plant-based polymers that can be converted into bioplastics. Keratin, gelatin, chitin, and chitosan are animal-based polymers that can be converted into bioplastics, while PHAs, mean polyhydroxyalkanoates, are microbial-based polyesters that can be converted into bioplastics. What are polyhydroxyalkanoates? Polyhydroxyalkanoates is a group of diverse group of polymers that may have more than 150 different types of monomers. And all these types of PHAs can be produced by microbes. On the basis of structure, polyhydroxyalkanoates can be classified into three major groups. First is the short chain length polyhydroxyalkanoates, which have 3 to 4 carbon atoms in their repeating units. For example, poly 3-hydroxybutyrate and poly 4-hydroxybutyrate. The second one is the medium chain length polyhydroxyalkanoates, which have 6 to 14 carbon atoms in their monomeric unit. For example, poly 3-hydroxyhexanoate and poly 3-hydroxyoctanoate. The third one is the long chain length polyhydroxyalkanoates, which are rare in nature and have more than 14 carbon atoms in their monomeric unit. This figure indicates how polyhydroxyalkanoates are accumulated in the cytoplasm of the microbes. And this is the basic structure of the polyhydroxyalkanoates, where N is the number of carbon atoms in this unit, while X is the number of the repeating unit, that is also known as the degree of polymerization. The degree of polymerization means the number of repeating unit may be 100 to 30,000. It depends upon the chain length of the polymers. Why we need bioplastics? This is the need of the bioplastic. These are the reasons why we need the bioplastics. These are the facts why we need bioplastics. About 395 million metric tons of the synthetic plastics are produced from petroleum sources, and this production is about becomes 3 times by 2050, as reported by the World Economic Forum 2019. The global plastic industry that have a birth of about 2000 billion euros in 2015 and increased more sharply up till now. This is the consumption of the synthetic plastics per person per year. About 109 kilogram of the synthetic plastics are used by one person in America. 65 kilograms of the synthetic plastic are used by one person in Europe, and about 10 kilograms of the synthetic plastics are used by one person in Asia. Synthetic plastics may take more than 10,000 years to degrade, not completely, but partially. An estimated 4.8 to 12.7 million tons of the plastics end up the world's oceans and seas. The extinction rate of marine life is 5 times higher than the terrestrial organisms due to the plastic waste and pollution in the oceans. The main objectives of this study was the production of PHAs by Pseudomonas under optimized conditions and the sustainable development of bioplastics using microbial PHAs can replace the synthetic plastics. First is the optimization, the growth parameters for the microbial strains as well as the production of polyhydroxyalkanoates. Temperature, pH, incubation time, carbon, nitrogen sources are optimized for the maximum production of polyhydroxyalkanoates. These are the conditions used for the maintenance of microbial strains as well as the preparation of the inoculum. Two microbial strains, Pseudomonas AK1 and Pseudomonas AK2, were used for the production of PHAs. Glucose, sucrose, and lactose were used as the carbon sources, while ammonium chloride, ammonium nitrate, and ammonium sulfate were used as the nitrogen sources for the production of polyhydroxyalkanoates. Two different dyes known as Nile red dye as well as Sudan black bead were used for the confirmation of PHA's production. After the confirmation of the production of PHA's, carbon source was optimized for the production of cell dry mass as well as the production of polyhydroxyalkanoates. These figures indicated the production of cell dry mass for two strains AK1 and AK2 of the Pseudomonas at various incubation time periods 24, 48, and 72 hours respectively. The carbon sources tested were glucose, sucrose, and maltose. These two figures represents the comparison of cell dry mass production as well as the production of polyhydroxyalkanoates at various concentrations of three different carbon sources. Figure 1 represents the production of cell dry mass and polyhydroxyalkanoates for Pseudomonas AK1 strain, while this figure represents the production of cell dry mass and polyhydroxyalkanoates by Pseudomonas AK2. Both figures represented that approximately high concentrations. High concentration 2% were you maximum production of polyhydroxyalkanoates were obtained at high concentrations of carbon sources. These figures indicated the optimization of cell dry mass production for two strains Pseudomonas AK1 and AK2. Three different nitrogen sources, namely ammonium chloride, ammonium nitrate, and ammonium sulfate, were used at 0.5% and 1% concentration. These figures indicated the comparison of cell dry mass production and polyhydroxyalkanoates production for two strains. From these two figures, it was clear that low concentration of nitrogen source, here is the approximately 0.5% ammonium sulfate is the concentration at which maximum production of polyhydroxyalkanoates were obtained by using the Pseudomonas AK1 strain. Similarly, AK2 strain showed maximum production of polyhydroxyalkanoates at ammonium sulfate. On the basis of these comparisons, our main target is the production of polyhydroxyalkanoates, not only the cell dry mass, but the major product is polyhydroxyalkanoates. These two figures indicated the optimization of temperature and pH for both strains. The figure 1 represents the optimization of the pH, which clearly indicate that the maximum cell dry mass was produced at high pH, mean at alkaline side, more than 8. Similarly, the temperature optimization graph indicated that maximum cell dry mass was produced between 38 to 40 degrees Celsius. After optimization, of various carbon, nitrogen sources, temperature, and pH for the production, cell dry mass, and polyhydroxyalkanoates. This strategy was used for the extraction of the polyhydroxyalkanoates. First, the sample was centrifuged at 10,000 rpm for 10 minutes. Then the pellet was suspended in sodium hypochlorite solution having a pH of 8 to 10 for 1 hour. Again, the solution was centrifuged at 10,000 rpm for 10 minutes. At this time, the supernatant was discarded and the pellet was washed with water, alcohol, and acetone. Then the pellet was dried at 60 degrees Celsius and then weighed. Here is the solid or powder form of the PHA extracted. The extracted PHA was confirmed by using the concentrated sulfuric acid and chloroform test. The change in the color from yellow to brown indicated that the product produced is the polyhydroxyalkanoate. Then the polyhydroxyalkanoate biofilm was produced by using chloroform by mixing the extracted polyhydroxyalkanoates with in chloroform, and then it was dried at 37 degrees centigrade for 48 to 72 hours, and the glycerol was used as the plasticizer. Then the extracted polyhydroxyalkanoate were analyzed by FTIR analysis. This figure indicated that the extracted polyhydroxyalkanoates from Pseudomonas AK1 and AK2 stains showed to be poly-3-hydroxybutyrates, which was confirmed by the absorption peaks. This peak represents the carbonyl group at 1725 per centimeter. This is the CH bond. This absorption peak represents the CO bond as well as OH bond and CC bond. This data represented that the extracted polyhydroxyalkanoate is most likely to be the poly-3-hydroxybutyrate. Here is the conclusion of this study. The indigenously isolated strains of Pseudomonas AK1 and AK2 have excellent potential for the biosynthesis of polyhydroxyalkanoates. Optimized parameters showed that PHA production is higher with an increased concentration of carbon source. Among the carbon sources, sucrose yields higher value of cell dry mass and percentage of PHA. Nitrogen concentration affects the cell dry mass, however, increase in its concentration decrease the percentage yield of the PHA. Nitrogen must be maintained at lower concentration up to 0.5%. Temperature higher than temperature range of 38 to 40 degrees centigrade is optimum for the PHA production. Similarly, higher pH more than 7 showed higher production of PHA. The incubation period is 48 to 72 hours. FTIR and protonic acid confirm the PHA polymer, and the monomer most commonly possible is the polyhydroxy 3 butyrate.